Hello everyone. So now I am here to throw some light on the topic of quantum numbers, which is prescribed in BSc Non-Medical Semester 1 paper Inorganic Chemistry. So in this video, we will discuss about the quantum numbers and the four types of quantum numbers in detail. Before starting quantum numbers topic, I would like to discuss with you all that now is the trend of online shopping. We all do online shopping, and when you select a product, what they ask from you is about your city, about your state, about your district and locality. Similarly, in case of electron, when we would like to have the address of the electron, we deal with this topic quantum numbers. This topic was firstly proposed by Bohr according to Bohr model of atom, and this quantum number helps to specify the position as well as energy of the electron in an atom. In wave mechanics branch of chemistry, Schrödinger wave equation was solved for hydrogen atom, and it was observed that the electron can be categorized or characterized by the set of three quantum numbers, that is N, L, M, and S. These are the designation for four quantum numbers, where N is for principal quantum number, L is for azimuthal or you can say subsidiary quantum number, M is for magnetic quantum number, and S is for spin quantum number. These all must be written in the small letter always. Let us begin with the principal quantum number. Principal quantum number is designated by the letter small n. This quantum number determines the mean energy level in which the electron is present, and it can have the integral values starting from 1 and tends to infinity, or you can say n can be varied from 1, 2, 3 and so on. Here in the table you can see that I have written when n is equal to 1, the shell number is capital K. So this quantum number can also be regarded as the shell, which in which shell number the electron is present can be determined by the principal quantum number. So you can see from the table when n is equal to 1, the shell will be K, and these names of the shells must be written in the capital letters. And for n is equal to 2, the shell number will be L, and n is equal to 3, the shell name will be capital M, and similarly when n is equal to 4, the shell name will be capital N. This quantum number also helps to find out the average distance of the electron from the nucleus and its energy. As you all know about the structure of atom, that nucleus is present at the center of the atom and the electron keeps on revolving around the nucleus. Now the second one is azimuthal or subsidiary quantum number. This quantum number gives the subshell or sub-level to which the electron belongs. Firstly, we have done about the shell, and now is the subshell, and it is designated as small l, and each corresponding value of n has the value of l which is ranging from 0 to n minus 1, or you can say the values of l must be varying from 0, 1, 2, 3, 4 and so on up to n minus 1, and this quantum number gives the energy of the electron due to angular momentum of the electron. Here in the table you can see the value of L varies from 0, 1, 2, 3 and so on, and their designation are written as under. For the value of L is equal to 0, the designation will be small l, or you can say the S will be the subshell, and when the L is equal to 1, the subshell will be P subshell, and when value of L is equal to 2, the designation will be small d, and similarly when the value of L is 3, the designation of the subshell will be small f. These subshells or you can say sublevels must be written in the small letters S, P, D, and F, respectively for L is equal to 1, 2, 3, and so on. These S, P, D, and F designations arises from the spectral lines produced in the atomic spectra. As you can see in the table, I have written the different values of N, L, and the subshell designation, and overall the number of subshells present in that principal quantum number. You can see I am taking the example of n is equal to 2. You can see for n is equal to 2, the L varies from 0 up to n minus 1. So here n minus 1 will be 1, right? So L has the values 0 and 1. And for L is equal to 0, the subshell designation is S and principal quantum number will remain same. So I have written the value 2S. Similarly, when L is equal to 1, the principal quantum number remains same, no doubt. But the designation will be written as, firstly, you have to write the principal quantum number, that is n, and here the n is equal to 2 and the value of L is 1 here. So I have written the designation of the subshell as small p. So there are two subshells, 2s and 2p. So that's why I have written the letter 2 for overall number of subshells in that particular subshell, right? These are the visual representations of different subshells, or you can say sublevel. The L is equal to 0 is s orbital is spherical in shape. Similarly, for p orbital, the dumbbell shaped I have represented, and L is equal to 2, the d orbital, the double dumbbell shaped I have represented in 3D or three-dimensional space. And similarly for L is equal to 3, similarly for L is equal to 3, the f orbital is represented. Now moving to the third one is magnetic quantum number. Now this quantum number describes the preferred orientation of the electron in the presence of magnetic field. As we all know that electron is a charged particle, or you can say negatively charged particle, and is always moving around the nucleus. So the movement of the electron is very much similar to the flow of the electric current through a loop, and this uh, movement will generate a magnetic field. As in case of wire, you can say when electric current is passed through a wire, it will generate a magnetic field in the surrounding area. Similarly, in case of electron, when electron is revolving around the nucleus, it will generate a magnetic field, and when we apply the external magnetic field, due to this interaction between the external magnetic field and the magnetic field due to the flow of electron, this results in the several orientations with respect to the applied magnetic field. The electron can can be present in different kind of orientations due to the interactions between these two kinds of magnetic field, right? And these orientations or regions of space occupied by the electrons are called as orbitals. For a given value of L, M has values ranging from minus L to plus L, or the total number of values for M quantum number, that is magnetic quantum number, which is represented by the small m, can have the total number of values as 2L plus 1, right? Here we can see from the table. Again, I am taking the example for n is equal to 2, where principal quantum number value is 2 and value of subshell will vary from 0 to n minus 1. Here n minus 1 is also 1. So I can say that L will vary from 0 to 1 and value of M will vary from minus L to plus L. So when I am taking the value of L is equal to 0, the M will be 0, right? And subshell is designated as 2S. But when I am taking the value of L as 1, the value of M, that is magnetic quantum number, will vary from minus 1, 0 and plus 1. Because I have already told you that the magnetic quantum number varies from minus L to plus L. So I am having the three values, that is minus 1, 0 and plus 1. And the designation of the subshell is 2 p. Here are some of the visual representations for all these orbitals. First of all, we are having the s orbital. In the second row, I am having the p orbital, which is having the three kinds of orientations, px and py and pz. Similarly, for d orbital, I am having the five kinds of orientations. These are designated as dxy, dyz, dzx, dz square and dx square minus y square. And in case of f orbital, we are having the seven orientations. Last but not the least is the spin quantum number. As you all know that electron is revolving around the nucleus, but it is also spinning on its own axis. Similarly, the case of Earth, we can say the Earth revolves around the Sun, but it is rotating it, uh, but the Earth is rotating on its own axis also. Similarly, in case of electron, the electron is revolving around the nucleus as well as spinning on its own axis. This spinning of the electron will generate a magnetic field in addition to the orbital motion of the electron. So we can say the electron is having the two kinds of motions. First one is orbital motion, that is due to the rotation of the electron around the nucleus. And also the second is the spin motion, that is due to the spin motion of the electron on its own axis. This spin quantum number describes the spin orientation of the electron and is designated as the letter small s. So the electron can spin in either of the two directions, that is clockwise as well as anti-clockwise. So we can have the two particular values for spin quantum number, that is plus half and minus half. The plus half I have shown in the diagram is due to the upward spin motion, and the minus half value is due to the downward spin motion of the electron. So here is the summary of our today's lesson, that is quantum numbers, four types: principal, azimuthal, magnetic and spin. And here is the diagrams for these four quantum numbers. In the first one, principal quantum numbers, we are having the different kinds of shells according to the model of the atom proposed by the Bohr. And second is the shape of the orbital, that is azimuthal quantum number, or we are designating these orbitals as small l. The third one is the magnetic quantum number, which is represented by the letter small m, and it gives the orientation of the orbitals. Last but not the least is spin quantum number, that is represented by the letter small s, or in some books we are having the letter m with the subscript s. This gives the orientation of the electron spin. I hope this video will help you to make this concept clear. Thanks a lot.